Guys, let's go ahead and get started. So first thing before we go on to review, I want to talk about equilibrium and acid-base chemistry real quick. So for equilibrium, there's one equation you need to know for equilibrium. Oh, it's someone is recording over here. Yeah. Okay, so for equilibrium, you need to know one equation, and that's KEQ equals your product over your reactants. So you guys have seen several equations today. You guys saw delta H equals reactants minus products. You saw Gibbs free energy, delta G equals delta H minus T delta S. And now you guys have seen this equation. 3 equations you need to know for the exam so far. Okay? So for equilibrium, a couple things you need to know. Things that are in the solid or liquid state do not change equilibrium, okay? So things that are liquid or solid do not change the effect on equilibrium. So we do not worry about them in our KEQ equation. We call their change, if it is any, equal to 1. Okay, so triangles change, we just say their change is equal to 1. Okay. Alright, so given the following reaction, I give you copper plus 4HNO3 goes to copper NO3 2 plus 2NO2 plus 2H2O. Okay. I give you the solubility, I tell you this is solid, aqueous, gas, liquid. Okay. And I ask you, what is the equilibrium equation? What is KEQ? Okay. So it's just your reactants of your products. You know if you have anything in the solid and liquid state, we do not include that. Lastly, raise each species to their coefficient. By each species, I mean raise each compound, raise each atom, raise each whatever to its coefficient. Okay. So KEQ is products of reactants. So I have copper nitrate. I see it's in the aqueous form, so I'm going to include that. And what power is this raised to? 1. Good. Next I see NO2. Okay. Raised to the power of 2 because I have a coefficient of 2. Lastly I see water. Do I include that? No, it's the liquid. Next I'm going to put it over my reactant. So here I see copper. Should I include it?
No.
Nope. Then I see nitric acid. Raised to the power of 4. And that's how you write an equilibrium expression, okay? And so you can, by looking at this, you can figure out what happens to my KEQ when I do stuff to it. If I add nitric acid, what happens to my KEQ? Does it increase or decrease? Decrease, right? I make the denominator bigger, so my KEQ will decrease, right? So you can figure out what happens to KEQ by setting up these equations. Okay.
Would that be on the final if I put more nitric acid in it? What will happen?
Yeah, so that's a fine way to think about what happens to KEQ as you change it.
Okay, I've never seen KEQ before.
Okay. Yeah, you guys talk about it in lab today and tomorrow. So.
Oh.
Yeah.
Tomorrow.
All right. So the next thing I want to talk about, for kind of delving into acids and bases a little bit. All right. So for your K, your K equals the negative log, your pKa equals the negative log of your Ka, okay? Or your KEQ, or your K of whatever, okay? Okay. So your pKa, this is how we determine what is the pH. Okay? So your pH is synonymous with whatever your pK is. So if I want to figure out if I am an acid, yeah. So for an acid, what do I want? Do I want a large or a small pKa? Small, right? So remember, for acids and bases on our scale, 7's in the middle, 7's neutral. Down here is 0, up here is 14. So down here is my what? Acids. Up here is my bases. Okay. So for an acid, I want a small pKa. This is the same as having a large Ka. Okay. If you're not sure, if you forget that property, that's fine. Just take the negative log of whatever your Ka is, and you'll get what your pK is, and you know that pK is the same as pH for this class. Okay? Does that make sense for everyone? Yeah?
What's the Ka?
So the Ka is the same as your KEQ, except you have different the subscripts. For instance, KEQ means K of the equilibrium, Ka means K of the acids, Kb means K of the bases. So what you can call K whatever you want it to be. In this case, I could ask what is the Ka, what is the acidic K, for instance. It's the same, you still do it the same way, it's just that we can label it differently. Good question. Yes?
Can you go over the acid thing again? Because, if it's a small pK and a large Ka,
It's a strong acid. Yeah, so let me write that here. So strong acid equals a small pKa, which equals a small pH, right, lower pH, which equals a large Ka. Because once I take the negative log of that Ka, I get a very small number, right? So that's how that relationship works. And if you haven't taken calculus yet, this might be your first introduction to a log. And if you're not sure how to use your calculator on the exam, you can always ask me after the review, and I can show you how to do a negative log or take something to the e power or something like that. Okay. Any questions about KEQ so far? Okay. All right, so let's make it harder. All right, so the next thing I want to talk about was, yeah, go ahead.
Oh, is what you said earlier, does that have to do with bases too?
Yeah, it can do with anything. Yeah, it's just that if I said KB, it means I'm talking about a base. So it's not something like, the only time you would know, for instance, whether you use Ka or Kb is like Ka would be I'm talking about an acid, Kb I'm talking about a base. KQ means I'm just talking about equilibrium. So it's just really how specific you want to be about labeling what your equilibrium equation is. Yeah.
So then if it was KB, would you want a large KB?
Large
Okay.
Kb, larger base, which means smaller Ka. So just the opposite of whatever those properties were for a base. All right, next thing for equilibrium, I want to talk about Le Chatelier. Le Chat. Okay. All right, so this guy basically said everything likes to be at equilibrium, right? So when I have a solution, it likes to be at some type of equilibrium. We've, for the most part, shown you reactions where I have A plus B goes to C plus D. That works for a very small handful amount of reactions in the world. In most cases, it's A plus B is in equilibrium with C plus D, okay? So almost everything in this world is in equilibrium with something else. Le Chatelier said, if I do something to one of the sides of the equation, something's going to happen on the other side because it's in equilibrium, right? It wants to be in this happy medium, okay? You guys worked with this a little bit in lab. So, if I say that A plus B is yellow, and I say C plus D is blue, what color is my equilibrium?
Green.
Green. So my equilibrium will be green. Okay, everyone know their colors? You can watch an episode of Barney if you need to refresh. Sorry, that's weird. Okay, so A plus C plus D, equilibrium is going to be green, right? Good. So what happens if I add D? What color will I see? Yellow. The reason why is equilibrium is like a swing, okay? The swing, when it's just sitting on the ground, nobody's riding it, is neutral. That's the equilibrium. When I start swinging the swing, I'm shifting its equilibrium, right? I add D, it's going to form a lot of yellow automatically. Then it's going to form some blue, and then some more yellow, some blue, some yellow, until finally it reaches green, okay? So that's how equilibrium works, right? Reactions aren't magical, okay? What happens is it has to adjust for the change that you induce until it can reach its equilibrium again. It's not just automatically going to turn green every time. As you guys saw in lab, when you added a solution, right where you added it, it probably turned really yellow, or it probably turned really blue. But then after a while, the color faded back down to that happy purple color. All right, so that's good. So what happens when I add A? Is it going to form product or reactant? Product. What happens when I take away D? It's going to make product, right? If I get rid of this, A and B are going to try to make the equilibrium again by forming more product. So I'm going to see blue. All right, let's make it a little trickier as everything is in chemistry. I tell you that I heat the solution. And it turns yellow. Is this reaction endothermic or exothermic? Okay, so how do we break this down? So I heat the solution. I add something to it and it becomes yellow. So which side is heat on? The product side, right? Because I heat it up, when I add heat, it shifts this way. It starts forming yellow. Does that make sense for everyone? You need to, just because I'm heating it up does not mean I'm adding a reactant, right? Because I could have a solution of A plus B equals C plus D and add C, right? Even though it's a product. It's a compound. It exists in the world. I can go buy C in a supermarket and add it to it, and then next thing I know, I add more product, right? Same thing. I added heat, causes it to shift to yellow, okay? Since heat is on the product side, I produce heat, typically. What kind of reaction is this? Exothermic, right? I give heat off to the environment. Because I'm giving heat off, I'm exothermic. Does that make sense for everyone? Okay, so simplest thing for these Le principles, the only three things you can do is 1, add a reactant or product. 2, take away a reactant or product. 3, add or remove heat. Okay? Those are the only 3 things you can do, okay? Everyone good on Le Chatelier? Oh, yeah?
Sorry. Would they give you heat, or would you assume the heat from the product, or could it be on the reactant?
It can be on the reactant. So if I tell you I heat the solution up and it turns blue, which side is it on?
Then it's
The reactant, yeah. Good question.
And it was exothermic because...
Because if heat is produced, it's exothermic, right? Because I give heat off to the environment. If heat is consumed, I suck it in, endothermic. I used an
because
example.
it was on the product side.
What?
Because it was on the product
Because it was on the product side because it was produced. Yeah. All right, and that's it for equilibrium. Okay, really short topic. All right, acids and bases. Acid on the new material. Some of you guys might have covered it for the last exam. Some of you guys might not have covered it that much. I just want to go over it just to be safe because it's on your study guide. Okay? So, for acids and bases, okay, so you guys learned several different definitions for acids and bases. So for an acid, basically for this class, you guys learned a nomenclature. It just has to have a hydrogen, right? And you guys had to memorize strong acids, and you guys had to memorize weak acids. Okay? For base, simplest thing is just to look for that hydroxide ion, okay? You see that hydroxide, you know that's a base. Okay? You guys also learned about some types of weak bases or weak electrolytes and that kind of thing. But for those, like, you just have to memorize the different trends. But ultimately, what it boils down to for this class is this is an acid, this is a base. And you guys memorize the strong acid, you guys know the strong acid. So, let's talk about conjugate acids and conjugate bases. Again, this is not the definition for all the different types of acids and bases. Depending on your instructor, you might have to memorize Bronsted, Lowry, what's the other guy? Lewis, acids and base, all that stuff. I think Dr. Small likes that, but I don't think Dr. DeWitt or Revels is going to focus on that. So, conjugate acids versus conjugate base. Okay. All right, so for conjugate acid, all you have to do is, so this is what you do, add a hydrogen. For this guy, to create a conjugate base, you lose a hydrogen, okay? That's all you have to do. So, if I have water, what is the conjugate acid form of water? H3O plus, right? Because remember, since this is at neutral, I'm adding a hydrogen, I'm obviously taking one of those electrons away from oxygen, it becomes H3O plus. So what is the conjugate base? OH minus, right? Okay. Alright, everyone see what I did there to figure out the acids and bases? Okay. So, conjugate acid, what does that mean? What is a more acidic form of water? Conjugate base, all that means is what is a more basic form of water? So if I give you HSO4 minus, what is the conjugate base form? 2 minus, right? Got rid of one of those hydrogens. What is the acidic form? H2SO4. Good. All right, let's do it again. SO4 2 minus. What is the conjugate acid? HSO4 minus, right? What is the conjugate base? Does not exist, right? Can't take away any more hydrogens. Can't make it more basic. I'm sorry, more, I can't make it any more basic than what this guy already is. Does that make sense for everyone? Okay. All right, everyone good on acid, conjugate acids, conjugate bases? Lastly, it mentions on there you do have to know those strong acids and strong bases. Okay, so that's something that you guys have to memorize depending on whatever your instructor said. Does anyone have any questions on the new material before I review the old material? No? Alright, we got a lot of old material to cover in an hour. Alright. Okay. Alright, let's start with exam 1. Guys, we're almost there. We got an hour to go. We can do this. I'm tired too. Trust me. I've been teaching Chem since 2 o'clock. Okay. Alright, so let's go over stuff on the first exam. First exam was basically talking about periodic trends. Let's go over those. Okay. Everyone remembers that periodic table I told you you should draw? Okay. These are our noble gases. These guys are always happy. Okay. Alright, up top, this top corner right here, this is where fluorine hangs out. This is the most electronegative. Okay. This has the highest ionization energy. Okay. Down here, this is francium. This has the biggest radii. This has the highest polarization. Okay. Oh, so what did they say?
D-E-A-R.
D-E-A-R?
No, D-E-A-R. Just go around clockwise.
Okay, starting here?
No, sorry, all the...
Okay. C?
Yeah, so it's like most basic.
Most basic, okay.
And then it would be like most electronegative.
Okay.
Then we most acidic, and then largest radii.
Sure, that works too, yeah. So if you want to, remember this is basic, acidic, up here electronegativity, down here radius and polarization, and ionization energy up top.
fair.
R is radius. All right, here we have our nonmetals. Here we have our metalloids. Okay. And here we have our metals. Okay. Everyone good on periodic trends?
Yeah.
All right, next thing you need to know for the atom. Okay. In the center, we got protons and we got neutrons. Okay. So remember, the mass, just your protons plus your neutrons. Okay. Remember on the outside, we got our electrons floating around. Ions. For an ion, that just means that you add or subtract electrons. Okay. For isotopes, that just means you change the number of neutrons. I put delta N, change neutrons. Okay. Okay. Structure this like elements complex. Okay, you need to know the location of everything on your periodic table, so you need to know where halogens, noble gases, alkali metals, alkali earth metals, all that stuff is. You guys can look on your periodic table from lab, and it says specifically what each column means. Electron trends. Okay. Everyone good on periodic trends? Everyone know that you have to memorize the columns on the periodic table? Okay, cool. Next thing you need to talk about electron configuration. Okay. So for this, it's pretty straightforward. You just look at your periodic table, such as this. You just start at the top left-hand corner. You work your way across, la 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 la, and then you stop when you get to the atom of interest. Okay. So for electron configuration, start at top left corner and move left to right. Okay. Second thing, stop at atom of interest. Third thing, put in numerical order. Okay. All right. So remember, guys, from the first review session, I said make sure that you put everything in numerical order, because if I ask you something like, what is the electron configuration for copper 2+, or what is the electron configuration for zinc 2+3, or something like that? That doesn't make sense. For +3. If you put it in numerical order, you're going to subtract the electrons from the correct orbitals. Okay? So let's pick an atom. I asked you, what is the electron configuration for silver plus? Okay. All right, so you just use your periodic table. You can use the last noble gas to start with, so you don't have to write the 1s2, 2s2 a million times. I see the last noble gas for silver is krypton. So I start with Kr. And then I go 5s2, 5s2, and then I go 1, 2, 3, 4, 5, 6, 7, 8, 9. So 4d9. Okay. But I asked for what it is for silver, not what it is for silver plus. So if you remember my rule, make sure you put this then in numerical order. So it's 4d9, 5s2. I tell you to take away one of those electrons. This is the correct configuration, along with krypton. Everyone understand what I did there? Just a review from the first exam. She says in big bold, be sure to review the electron configuration for transition metals, just like I did right now. Yes?
So why are the DNS swapped?
Because you want to put it in a numerical order. So remember the subshell, so you go level 1 first, level 2 first, level 3, level 4.
Oh.
So 4 before 5. Yeah.
Can you do an example between the D block and the S block? Like the one right after the S block?
Yeah, but you don't need to know that. If you want me to go over it, I can. Okay. Yeah, so you don't need to know anything below row 5. Yeah, so you wouldn't have to worry about any of those last 2 names or after names. Oh, your teacher gave you a quiz question? That's messed up. You don't need to know that. Yeah. Who's your instructor?
Desiree?
Oh. All right. Energy level diagrams. Simple. It's almost the same thing as filling in the electron configuration, right? So you know that you have 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, going upwards, 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 and then you just put in your electrons the same way we did. If you see you have 1s2, 2s2, 1s2, 2s2. Remembering you have to follow your rules, Hund's rule, Pauli exclusion principle, and off-balance, okay? You need to fill up all those levels first before you can go to the next one. Make sure you fill up each one of those little orbital boxes before you go back and before you start pairing. And off-balance lastly says that make sure they have opposite spins. Everyone good on those? Okay. Off-balance, opposite spins. Oh, sure. All right, off-balance, or no, sorry, Pauli, opposite spins. Hun, fill up energy level before, this is Hun's, right? You guys? Yeah. Hun, okay. Before moving up to next energy level. Okay, and then lastly, off-bow says put one electron in each orbital before pairing. Everyone good on those definitions? Always mix up Hunt and off-bow, so is that right?
Yes.
Yes. Thank you.